Hello, my name is Dmitry and I will present the first developments of our ongoing project aimed at providing a formal model for complexity of programs in miniKanren. For now, there is no such model, and when analyzing performance, a programmer is usually relies on time measuring for specific instances. This way, we have to guide program design by some known examples and heuristics rather than general understanding of the search. So the examples with surprising behavior will arise from time to time. Let's consider the following example comparing two definitions of the relation computing the length of a list. Naively, we can define it as this way, just taking an imperative definition and transforming it step by step into the relational form. But to get this conventional definition, we have to move the recursive call to the end. This way, we will execute all the constraints before the recursive call, and the program will be suitable to be run backward. But let's measure time for inputs of different sizes if we use this relation as a function to compute length. You can see that the naive version is significantly slower, although it performs adequate steps in an adequate order. The difference is even more striking if we disable a curse check in unifications. In this case, the dependency for the naive versions seems to be linear, while for conventional version, it's obviously not non-linear. If we look closer at the unifications performed, we will see that there is no reason for this difference, and the reason is somewhere else. In this project, we want to build a formal model to be able to understand such behaviors and be able to predict them. This model should include different parts of the search. Abstractly, search in miniKanren can be decomposed into the following three parts. Scheduling, that transforms relational execution into a sequence of unifications. Performing the unifications, that involves occurs checks by default, and verification of the answers at the end. So the overall time can be decomposed in these four components, and it's actually the component of scheduling time that is responsible for the difference for the length example. Notice that we separate time of occurs check because, as we've seen in the previous slide, it can make a huge difference, so we want to be able to detect it. Our goal is to construct a model that provides formal characteristics for all these components of time and can be applied to estimate their complexity for a given program. We have to choose some version of miniKanren as a basis, so we are focusing on the conventional on the canonical version that is described in the book The Reasoned Schema. For now, we have a model, but it's only can be used to estimate the time of the full search when we're asking for all the answers, and for a limited class of programs, including many practically interesting ones. The rest of the talk is structured as follows. First, we will discuss methods to estimate time for different parts of the search separately. Then I will informally describe a technique that brings these methods together to estimate complexity of a given relational program using symbolic execution. And finally, I will present results of evaluation of our approach for some known examples and some observations on these results. Let's start with analysis of scheduling time. To analyze the behavior of the search, we rely on an existing operational semantics for the interleaving search. It's a deterministic label transition system with partially evaluated search trees as states. Leaves are the goals. Leaves are goals we need to execute, and nodes correspond to M+ and bind. Evaluation is of the relational program is defined by the path along the transition in this transition system that is called trace. As a first approximation of the scheduling time, it's natural to take the number of transitions in the trace, which corresponds to the number of forcings when traversing a lazy stream. However, each of these transitions does not necessarily take a constant time. Actually, each of these steps involves navigation to the leftmost leaf to find a goal to execute. So, a better approximation of scheduling time is a sum of depths of the leftmost branch for every state in the trace. We derive recursive formulae for this value that we call the scheduling factor for M+ states and bind states. And the exact equations, recursive equations, are rather cumbersome to use directly, and we also have some approximations that are convenient to use. It's worth noting that to use formulae for bind states, we need to know all answers produced by the search for a substate. We will use this recursive formulae to estimate scheduling time in the future. Now let's move on to analysis of unification and reification time. In general, the time of unification is hard to estimate precisely, and it can be exponential in the worst case. But the majority of instances that we meet in logic programming are simple and can be solved quickly, even by the simplest unification algorithm. For this reason, sometimes in logic programming, unifications are regarded as basic operations that take constant time. We want to have this advantage too, but also we want to describe our model more rigorously, so we formulate two dynamic criteria for execution of programs that ensures that unifications are simple, and we consider only the programs that satisfy these criteria. We consider the Robinson's unification algorithm with triangle substitution that is conventional for miniKanren, and estimate time of a curse check separately. Both unification and reification performs some basic operations on substitutions. And first we need to determine the time of these operations. Time of lookup and add depend on the data structure we use to represent substitution. Different implementations of miniKanren uses different data structures, but in all practically applicable ones that we know of, lookup and add have logarithmic complexity or less. So we can, and as we expect complexity of relational programs to be polynomial or even bigger, we can regard these operations as basic and actually count the number of them to estimate unification time. Another basic operations that are specific to triangle substitutions is walk, that finds a value for a variable in the substitution. to do it, it may need to go through a chain of variable-to-variable bindings. So in the worst case, its complexity is linear on the time or on the size of the substitution. But in our experience, the variable-to-variable bindings are quite rare in practice. So as a first criterion, we impose the absence of such bindings during the evaluation. Under this condition, the time that the number of under this condition, walk takes a constant number of lookups. The Robinson's unification algorithm is a simple recursive descent on terms unless some variables are updated during the process by bindings that are found by the bindings that unification adds to the substitution. Again, we suspect that this situation is not so usual in relational programming. So as a second criterion, we require that all unifications during the evaluation are linear, meaning that every variable occurs in the terms at most once. Under this condition, the recursive descent only goes to the closest variable, so the number of basic operations it requires is bounded by minimum of sizes of terms. If we then perform accursed checks, we need to go through the rest of the terms. So minimum in the estimation changes to maximum. And the reification simply goes through all terms for all answers at the end. So the number of basic operations it requires is proportional to the total size of all answers. Now that we discussed methods to estimate different parts, the time that different parts of the search takes in general, let's move on to a technique that brings them together to estimate a complexity of a given relational program. But first we need to state the problem formally. Complexity is a function that depends on some parameters of the input. And to denote these parameters, we use symbolic variables. Symbolic variable can be regarded as some ground term which represents an object from some meta theory depending on the relation. It can be a number, a graph, a string, or anything else. And then we ask a question of this, a question like this: how much time, depending on the list L, does the different parts of the search take for the following query, where we specify the first argument with the representation of this list L for length relation, and ask for the second argument. We then can calculate complexity within the meta theory, and the answer can contain notions from the meta theory too. For example, complexity of scheduling time depends on length of a list. The technique we propose contains the following stages. First, we run the body of the relation symbolically and construct so-called symbolic scheme, which explicitly shows all the information that the methods of estimation described before require. We then check the criteria for simple unifications on this scheme, and if they are satisfied, extract the recursive inequalities for the for the all components of the time of the search using the estimation that we described before. Then we can solve these inequalities within the meta theory to derive the complexity of a given program. Let's take a brief look at the specific example that analyzes of how we would analyze this query computing the length of a list using naive relation. The symbolic scheme corresponds directly to the body of the relation, but it also shows all the answers that are transmitted through the search in forms of bindings that are produced by sub-goals. And it also shows the values of all the terms at the point that they are evaluated. We can then, on the scheme, we can easily check the criterions and go through the scheme to applying our estimations directly to extract recursive inequalities for different components of the search. For example, for time of unification without accursed checks, we extract the following inequality. It can look rather complicated, but if we consider two cases when list is empty or not, we get these two simple inequalities from which it is evident that the complexity of unification is linear on the length of the list up to a logarithmic factor. The detailed description of how the process of constructing scheme and extracting inequalities works can be found in the paper. And for now, the technique that we described has a number of limitations. First, we only have informal descriptions, so we can't automate any part of the process. Second, we need an oracle that will tell us the answers for internal relational calls. So before analyzing the time of the complexity of relational programs, we need to know which answers are produced by the search. And also, as I mentioned before, we can only analyze the full search and only a certain class of programs that satisfy criteria for simple unifications. We applied our approach for a number of known examples. Specifically, we took relations for operations on numbers and lists and ran them in different directions. All these examples satisfy requirements for our technique, so we were able to get complexities, and in all cases they are polynomial. Here are just some of the results. The full table you can find in the paper. From looking at these results, we take these two observations. First, occurs check are really to take a huge role in the overall time. In all cases, the complexity of this component dominated all others, and in most cases, the presence of accursed checks increments the degree of the polynomial for the overall time. And the second observation is that position of the recursive call makes a huge difference for scheduling time. And because of it, we can see some surprising behavior, like the fact that sometimes running relation backward is faster than running it forward, as is intended. For sanity check, we performed some actual time measuring for these examples for an exemplary implementation of miniKanren. We got graphs like this one for overall time, depending on each parameter for each query. It's hard to get a specific character of dependency from these graphs, especially because the precision we are able to achieve is rather limited. But after studying them in detail, we haven't found any example that violates our predictions. This work is still in progress, but we have already got some results and interesting thoughts, and here are a few of them. First, we can use help. First, a formal model for time complexity can help us to understand some strange behavior of relational programs and may guide program design and language implementation. Second, symbolic execution can be handy to calculate some characteristics for recursive relational programs which depend on parameters in the input. And finally, complexity study confirms some common wisdom for miniKanren programming, like the fact that that occurs checks are expensive and you should omit them if possible, and that sometimes placing recursive call in the end can make things better. That's all. Thank you.